Ready? Let's do it. Today's lecture, the first part, is entitled Maxwell's Equations. We're going to put all of the pieces together. Right now, you are 7th level field masters. You have become that. I now confer that status upon you all by virtue of your performance on the last 2 tests. You are now 7th level field masters. Now that we can walk, we're going to start to run on this lecture. We put all the pieces together. And in doing so, we recount one of the greatest scientific synthesis of concepts in the history of mankind. It's actually a pretty neat lecture because we get to put all the pieces together, just like James Clerk Maxwell did back in the 1860s when he was working on this. Keep in mind, this is about the time of the American Civil War, almost 150 years ago now. And we will get to see him step through what he was thinking as we put this system of equations together and perform what we call a synthesis. That was taking a bunch of things that were known, polishing them up a little bit, putting them together, and discovering something new. This is really neat because using the power of the theoretician, the power of the pencil, he's getting down on a piece of paper, putting everything together. And what we'll be seeing, especially at this lecture and then the next segment, how in a way he's calling into existence all of the modern technology we're using today. How do iPhones and smartphones transmit to cell towers? How do Ethernet cables work? How do anything electronic work? And to that end, this is actually going to be one of your exam questions that I will put the answer on the board as we work through this lecture today. The question will be memorize and recount Maxwell's equations, both in integral, differential, and word form, and describe the name and the units given to all the variables in that system of equations. That's it. That is 50 free points. I just give it to you. Out of maybe 150 or 200. But still, it's a substantial portion. If there is one thing that Georgia Tech students know how to do, it's memorize the hell out of something. And I'm counting on that. I'm counting on that. So, it's not easy. There are still people that will make mistakes, silly mistakes. They'll either forget to study, or they'll forget their units. But that's right. And I'll give a little crib sheet online with my answers. All you got to do is just spit it out. Well, a few times you can get away with that in this class. So that's Maxwell's equations. So let's go through first and say, what is it that we know? What is it that we know so far in this class? Well, we know Coulombs Law, which says that a closed surface integral of electric flux density vector is equal to the volume integral over the volume that surface encloses of charge density. Volume charge density. So let's pretend this was the test. Let's pretend this was a test. And I'll go through, this will be the integral form part of the paper. This one will be the differential form. So let's all label this properly. Maxwell's equations. And my corresponding Coulombs law that I've written there in differential form, we know this to be the divergence or the sourciness of the electric flux density vector is equal to the charge density, the volume charge density. Remember, coulombs per meter cubed. Electric flux density vector is coulombs per meter squared, and when you differentiate it with respect to position, as this operator does, you get coulombs per meter cubed. It's like dividing through by a meter. And then let's go over here. and write the word form. And this may be one of the most important things to know from this class, besides the equations. Because the word form lets you explain it to other people. What does that mean? Does anybody want to take a crack? What does that equation mean in word form? How would you describe this? Randy, do you want to give a try? I saw your hand bravely go up and then shrink down really quickly, so I'm going to pick on you. You can do it.
The gradient of the density is equal to the surface. to the volume charge.
Yeah, that's right. The gradient of the electric flux density is equal to the volume charge density. But you really just read the equation. Yeah. What does it mean? What does it mean? It was like that. No, I had a physics teacher in high school who was going over Newton's law. Did I ever tell this story? No? Okay. He said F equals ma, and somebody said, "Well, sir, what does that mean?" And he looked at it, and after a minute of thinking, he says, "Well, it means F is equal to ma." And then he continued onward. Thanks a lot. No, it's hard though, because how would you explain this to somebody who wasn't so technical, who wasn't an electrical engineer?
The difference in concentration.
Somebody who didn't understand science, like maybe an industrial engineer. No. That was caught on tape. Oh crap. So.
Isn't the gradient the sourciness?
That's right. The sourciness. Alejandro, go ahead.
Can we say that what's actually coming out of a surface, around the surface, is actually what's actually inside that volume?
Yeah. That's kind of like that's a good way to describe the integral form. It says the same thing, but that's really my joking explanation of Gauss's law, right? It's what's inside that counts. Electric flux comes out of positive charges and goes into negative charges. So, you can tailor this however you like. The expression that is kind of succinct and communicates very clearly with an economy of words what that equation means is this. Electric charges spawn electric flux. I like that word spawn, like the salmon. Well, what does spawn mean? It means come out of, right? Kind of. So positive charges spawn electric flux. Negative charges actually sink electric flux. They do the opposite. That's why they have the opposite polarity. And that's fundamentally what those equations mean. Electric field and hence electric flux comes out of positive charges and goes into negative charges. Starts on positive, ends on negative. That's all it means. And the equations really just give that a little bit more mathematical structure and rigor. But that's fundamentally what it means. Okay, so that's one thing. And what was that called? What was that individual law called? That we studied at the very first lecture after transmission line theory. Coulombs Law. This is all really just a different statement of Coulombs Law. Or Gauss's law applied to Coulombs Law. Okay, good. So we know that. Let's see, what else do we know? Let's go over to here. Maxwell's equations, integral form. And let's see, what else do we also know? Ooh, here's a good one. Ampere's law. If I take the integral around a closed path, a line integral, this is where we're counting magnetic field vectors, the collinear part that lie tangential to an enclosing path, then that must be equal to the enclosed current. And we can write the enclosing current as a surface integral that this line integral goes around, surface integral of my current density vector dotted into the surface normal differential element of integration. Of course, we all know this to be the current, I, where this is amps per meter squared. This is amps. This is amps per meter, and when you integrate it with respect to position, it just becomes amps. So you have amps equals to amps. Everything is satisfied. That's another elegant little integral form. And of course, we also know that has a differential form. We can apply Stokes' theorem, and we can pull out the interior parts of the integrands, and we get that the curl, or the swirliness of H, is equal to the current density vector. I always like these differential forms of Maxwell's equation because they're so succinct and cute. They weren't actually succinct in Maxwell's original treatise. If you go back and look at his original work, he actually wrote this operator out longhand in a lot of his equations. So he'd have partial derivative with respect to x, y, and z operating on the x and y and z components of H. So you actually have 3 sets of equations, each spelled out with their partial differential operators longhand. It wasn't until Oliver Heaviside came along a few decades later and kind of cleaned this up in a textbook on Maxwell's equations that he was working with. And we are all the beneficiaries of that, right? So,
Dr. Dargan?
Oh, yes, Bill from Savannah.
Yes.
Is that my friend Bill?
That is true, yes.
Oh, good. Thanks, Bill. What can I do for you?
I've got, it's just that since the units are part of it, and when we would put the units on the Coulombs Law, we know that, of course, it's charge, but
That's right.
then would we also have to include the flux density? Or the...
Yeah, I'm actually going to, I'll need to erase one of my boards at the end. But at the end, I promise I'll write down also all of the variables that we used and then their corresponding names and charge units, just like you're expected on the test. So the only reason why I'm not doing it at the moment is because I'm running out of board spaces. I got 3 already, and then there's that little one at the corner that's no good for anything. So good question. And if I forget, I won't. But if I do, come ding me again in about 20 minutes. Good question. Okay, so who wants to try this, to describe this in word form? How about Bill from Savannah? Because nobody from Savannah ever chimes in to respond to my rhetorical questions. And Bill, you're the only one I know out there.
Could you repeat the question?
Oh, yeah, sure. No, this is how would you describe this equation in word form? Give it a shot.
The swirliness of the magnetic field is equal to the moving current enclosed?
Yeah, that's great. That's great. Let me put it over here. I'll put my version, which says almost the exact same thing. Good job, Bill from Savannah. Everybody, thank you for being my volunteer, my willful participant. Magnetic field swirls around current. We'll call it electric current. Or if you want to be a little maybe more technical, swirliness doesn't cut it like at the technical conferences and that sort of thing. You could say circulates. Circulates. That's just the right-hand rule, right? Magnetic field circulates around current. Now this one isn't quite done yet. I shouldn't put a period there, because we're going to add one thing to that a little bit later, a little qualification. Okay. And then we go over here to Maxwell's equations. And we also studied Faraday's law, which says E field, the closed form E field integral around a path that closes in on itself should be equal to minus, let me write it like this, minus partial derivative with respect to time. I'm not giving myself enough room. We'll just do it like this. Minus the partial derivative with respect to time of the flux integral. So you take the surface integral over the surface enclosed by this line path, and you add up all the magnetic flux density. You make a flux integral. You take the time derivative and the total voltage around that path, the cumulative E field that is tangential to whatever path shape you're integrating around, which of course we know to be a voltage. This is volts per meter integrated along distance to give volts. That is going to be equal to the time variation in the magnetic flux of enclosed by that path. That is Faraday's law. Faraday's law. And of course we know we can apply Stokes' theorem to that. We did that earlier in the class, and what we got was the curl of E field is equal to the time derivative of the B field at any given point in space. Remember, these are all functions of three-dimensional space. I haven't written them as such. You know, they should all be functions of that R vector, x, y, and z. X, y, and z, function of 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 x, y, and z. I'm just omitting that because it just gets tedious to put parentheses R vector or parentheses x, y, and z at the end of all these things. So yeah. Now, who would like to try the word form of this? How would you describe this? Carter.
A changing magnetic flux will induce the voltage.
Yeah, that's good. That's good. Changing magnetic flux will induce a voltage. Another way to put that, and that would be fine. I would give you full credit for that. If you wanted some symmetry with the one we came up here, is that electric field circulates around changing magnetic flux. And we know that is the process of induction in the physical world. So these were all the things that we knew at the time that Maxwell came along and started to heavily invest in this problem, trying to figure it out. And these were kind of disjoint pieces of information. We had Coulomb and a bunch of other people looking at electrostatic charge and how to describe that. We had this magnetostatic relationship that Ampere was kind of working with. We had Faraday's law, he's sticking magnets into coils and seeing light bulbs light up and things like that, or electric or work being done, galvanic potential jumping up and down as he changed the flux through a coil. And so he looked at this, and he kind of arranged things in this form. And he said, you know what? I kind of used the principle that, you know, the physical world should have some beauty to it, a little bit of symmetry to it, too. You know, we wouldn't necessarily expect that, but yeah, you know, why not? Why not have some beauty in the way that the laws are written here? And we look over at this system, and you think, well, what's missing? What's missing? We have this kind of Gauss's law relationship or Coulombs law relationship for electric field or electric flux density. It says, is it not reasonable to think that we should have a similar relationship for magnetic flux density? In other words, shouldn't you have an enclosing surface integral to count magnetic flux coming out And shouldn't that be equal to something like, if you wanted some symmetry in the deal, the volume integral of magnetic charge? But wait a second. Up until this point, and at no time period thereafter, have we ever observed a magnetic charge? So one of the key contributions that Maxwell made to kind of close the loop in all of these equations that he brought together was to come over here and said, you know what? We haven't seen anything like a magnetic charge yet, so this must all be 0. This must be 0. And in fact, because we haven't seen a magnetic charge, you know, in a way, we've got this thing called electric current up here. We could, if we wanted true symmetry, we could add some magnetic current in there too, right? That would kind of, then the laws would kind of match, you know. You'd have electric current would cause magnetic field to circulate around it. And we're tempted to think, oh yeah, if there was something like magnetic charges and they were moving, you'd have electric fields circulating around that. But alas, because we have never observed a magnetic charge, it would be foolish to think that there would be magnetic current at this point. And so, well, let's just leave it off. Let's set that categorically equal to 0. So this law is now complete. This law is now complete. And we just added a little 0 there because we haven't observed charge yet. And the last thing that Maxwell did was to change Ampere's law, add what initially was kind of like a fudge factor, but it actually makes a lot of intuitive sense. And that was this. He looked at this and said, well, here we've got time variations of magnetic flux inducing a voltage around a path. It would probably be reasonable to think that you could induce a magnetic field around an enclosing path proportional to time variations in electric flux density. So you take that same surface integral, you count the electric flux going through it, just like you did the magnetic flux for Faraday's law. You take the time derivative, and you should get a magnetic field that circulates around it. You know, you can almost make that inference that should be there just based on the beauty of the mathematics, right? Oh, let's make this law look like this law. And yet, it turns out that solved a very important paradox in physics at the time. And it was called the Capacitor Paradox. So if you go over here, let me just sketch a capacitor for the moment. Let's say you had this circuit element that was a capacitor. You had current flowing into and out of it. And of course, we know that current flowing into and out of the capacitor is really positive charges building up on one plate and negative charges building up on the other plate. Of course, in this case, it's negative electrons depositing up here and then depleting this piece of metal up here in physics. But this is how we mathematically represent the scenario. And of course, this was always a little bit of a disturbance to the scientific minds because at first blush, the old Ampere's law didn't work for this system, right? You had a capacitor, there was current flowing through here, but if you did an Ampere's law integral around the wire that carried that current, do a right-hand rule. So let's say this is going this way. Current's going down here. Magnetic field should circulate around that wire. If you did that on the lead going away from the capacitor or the lead going into the capacitor, you'd always get a perfectly behaved Ampere's law. But if you were kind of like one of those smart alecky kids that always ask the really difficult questions, and immediately your hand went up.
That's me.
What is your question?
Oh, no. I was just saying I'm a smart alecky kid.
Oh, okay. Yeah. Thank you for that. If you took your Ampere's law integral there, something bad happened. There was no current flowing through here. No physical current. There couldn't be. It was a vacuum. And yet, if you were to measure the magnetic field, just because you were taking the integral down here instead of up here or down there, it would still be the same. It would still be the same. And the neat thing is, by adding that last term that we just did, Maxwell solved what was called at the time the capacitor paradox. The capacitor paradox. Because what he says is, in his construct that he put up on the board there, he said, well, there are two types of current. There's physical current, which is the J vector, the charges that are moving in the system. And then there's this other term, change in electric flux density, which he called displacement current. Partial derivative of the electric flux density vector with respect to time. And we can see that's a really nice way to do it. Because if charges are depositing, positive charges are depositing up here, negative charges are depositing down here, there should be an increasing, with respect to time, electric flux density vector between these two plates. And as that increases, the time derivative will effectively be the current that balances out Ampere's law equation. It's also the current that balances out the Kirchhoff current law. You remember taking that in your circuit theory class? You could draw a circle around this and call this a node and say, well, the current coming in up here has to be equal to the current going out of that node. And so, well, what if you were that smart alecky kid that says, well, professor, what about if I draw my node like that? Well, it says, Kirchhoff's current law works fine, provided that you use displacement current to balance it out at that point. The change in the electric field, rather than just the physical charges. And at first blush, that looks a little bit like a fudge factor, doesn't it? Oh, let's just kind of append this to Maxwell's equations, to Ampere's law, just to get it to work out. It's interesting that when you look at Maxwell's equations and kind of consider it in that form, you get a really nice affirmative result that comes out of this that we've actually seen before in this class. So let's go over and append the differential form of that term to Ampere's law. Curl of H is equal to J via Stokes' theorem. Well, it turns out this is also, you can also apply Stokes' theorem and show that this is the partial derivative with respect to time of that electric flux density vector. And now there's something you can do if you start combining Maxwell's equations. Let's take a look over here. I am going to take the divergence of both sides of this equation, so that I have the divergence of the curl of H, and that should be equal to the divergence of J plus the divergence of the time derivative of that vector. Of course, the time derivative of a vector is always a vector, right? You're just taking the partial derivative with respect to time of the x component, you're sticking it on the x, the y component, sticking it on the y, the z component, sticking it on the z. Now, a couple quick little sneaky manipulations. This is a partial differential operator with respect to space. It's linear. It does not do anything with respect to time. This is a little partial derivative with respect to time. That's also a linear operator, and it doesn't do anything with respect to space. So I can commute them. And I can write this. I also go over here, and there's a basic mathematical identity that we can apply to this. When I take the curl of a vector that operates on a vector field and gives me a vector field that represents the swirliness of the system. When I take the divergence of swirliness, what does that give me?
Zero.
Zero, that's right. And that's a mathematical property. That has nothing to do with the physics. Any vector that you take the curl and then the divergence of, you get zero. A scalar zero as the result. So what this really means is that my divergence of current is equal to minus the time derivative. And instead of writing the divergence of electric flux density vector, I'm going to substitute this Maxwell's equation in there. Charge. Now, this is often reported as the fifth Maxwell's equation, but it's actually a derivative from the two independent ones that we've written up here. This has a special name, and it's called the continuity equation. But really, all it says is that charge is conserved in the world, which is another very gratifying result. And we wouldn't have gotten there without this term added to Ampere's law. Why does it say that? Well, look, sourciness of electric current. If the sourciness of electric current is 0, that means there's no source of electric current. Current can just flow around and be 0. But if it's emanating from an area, then clearly you're smuggling extra charges at the source of that current to supply the current with the charges it needs to move. And if that's true, then clearly you are depleting the volume charge in that same space. That's all this means. If this term was 0, then what would happen is the divergence of J is always equal to 0, which means you always have electrostatics or magnetostatics. There's no ability to start and stop currents. And there's no charges. If you were to do so, you'd have to have charges materialize out of nowhere. So that's a gratifying result. That kind of gave some confirmation that Maxwell's intuition for synthesizing these various different behaviors of electromagnetism that were being observed by researchers all over the world, he was able to verify that that synthesis was correct, in part by the derivation of the continuity equation. So let's now complete everything because we've got it all. Here, the Gauss's law in differential form, divergence of B is equal to 0, because we said there is no such thing as magnetic field, magnetic charges, and in fact, we can write the word form of that as well. There are no magnetic charges in the universe. A lot of times you'll hear physicists call this magnetic monopoles. Monopole is just a charge. A charge. So Maxwell's equations, word form, there are no magnetic charges in the universe. And I have to go append a little bit to this one as well. The magnetic field circulates around electric current and changing electric flux. And that's it. That's where we go to. Now let's do the mundane exercise of writing out all the variable names and units that we have used in this system. E field is electric field, and it has units of volts per meter. H field, we electrical engineers call this the magnetic field. The physicists call this a 4-letter word. The B field, this is the magnetic flux density to us electrical engineers. This is units of Webers per meter squared. A Weber is a volt second, actually. D vector, we call this, the official name is the electric flux density. Units of coulombs per meter squared. J is current density. units of amps per meter squared. And rho sub v is volume charge density. Coulombs per meter cubed. Let's see, is there anything else that I should write there? Did I miss any terms, any variables? I think we got them all. Everything that we used. Now, of course, there are some constitutive relationships, you know from your physics class, that V is equal to permeability times H vector, and D is equal to permittivity times your E field vector. But of course, these are material parameters that relate the two vectors to one another. They're sort of part of the boundary conditions. You know, these are what I put here as Maxwell's equations are the governing differential equations of electrodynamic systems. And these are kind of talk about the boundary conditions and the different materials that you can have that relate the fields together. So yeah, Justin.
I have a question. It's kind of abstracting this, but
yeah, sure.
From the four equations, it's almost to compare it to something not in engineering. It's like we're looking at, in the first one, we're looking at a blood cell and studying how it moves. In the second one, we're studying like a small stream within the vein. And then the third one, we're studying how blood flowing in veins affects cellular tissue. And then the last one, we're saying that you can't really affect anything outside your body.
That's an interesting analogy. I have to think about that one for a little bit. Interesting. Interesting. I think you could probably draw a lot of analogies here, especially with things that flow, turbulence, air flows, water flows, that kind of thing. Lam, do you have a question or a comment?
I had two questions about like the word forms. Like, like you said that before, there's electric charges spawn electric flux. Like when you start talking about things in the universe and it starts spawns like nothing, that does are you saying like electric charge or electric flux follows charges, or like follows it kind of like a puppy in a leash, or is it
I think it would be more accurate to say this. The electric field, as we've defined it in this class, is sort of a physical construct or mathematical construct. The actual physical thing that you measure is force on charge, which is always proportional to electric field. Electric field times the charge in coulombs is the force on that charge, that particular charge. So that electric field, that mathematical construct that we use to track the charge forces in a system, is, I use this word spawn because it's kind of graphical. It kind of shows you if you can kind of visualize the vector field in your head, pointing away and diminishing as you get away from the electric charges of the system. So if I got a charge, like a point charge, like Coulombs Law says, I should have electric fields radiating away from that. Now, are there fields that are actually traveling around? That's debatable because it's a construct that we use to track forces. And I would need about another lecture or two to delve into the finer details of that statement.
The magnetic there's no magnetic charges in the universe?
That's right.
Like gravity? Gravity's not, I know.
Gravity is a completely different force.
But just no.
There are. We haven't observed any in thousands and thousands of years of physics and observing the universe, so we're pretty certain that there aren't any. In fact, if you remember back when we talked about currents and charges, all magnetic forces can be explained as electric forces observed with a relativistic change in your reference. Yes.
Oh, okay.
And so as a result, now I should say this. You will know when you have arrived in life and you have become a 7th level wave master when you work problems in which you intentionally introduce magnetic charges and currents. If you take a higher level electromagnetics course, your instructor will add terms to Maxwell's equations like this. And that is for mathematical convenience. It's really cool. Like, this allows you to solve some problems mathematically that you can't solve without magnetic currents and magnetic charges. You're like, why do you have to make stuff up to solve a problem? I don't know why, but it just happens to work this way. That if you introduce magnetic currents and magnetic charges, you can do things like apply something called the equivalence theorem. I used to do this all the time in radar theory. So you send an electromagnetic wave in radar and it strikes an object, and you want to figure out how does that object reflect the waves. Well, when that nice clean plane wave strikes an object, all hell breaks loose. And you start spraying waves in every single direction with different polarizations, different amplitudes, different phases. And it's important to model that, especially if you're trying to design a stealthy fighter or you're trying to back solve the radar cross-section of an enemy fighter plane or something like that, or a missile. And it turns out that to solve that problem is very difficult, because to solve Maxwell's equations in a system that is not homogeneous free space is extremely difficult. And by virtue of the fact that you have something other than free space, like a missile or a plane or anything hanging in the middle of air, you've actually made the problem extremely difficult to solve. Unless there's this theorem that says you can replace that missile or airplane or parachuter or whatever with equivalent magnetic and electric currents that will behave exactly the same, but you may then solve that system in free space. That's called the equivalence theorem. And so all you got to do is just, if you want to measure my radar cross-section and you want to simulate this numerically, what the old radar guys would do, they'd code up their field solver, and instead of codifying a really complicated conductive saltwater mass shaped like Professor Durgan into their system, what they would do is they would replace me with surface magnetic and electric current. You can only apply the true equivalence theorem by using both electric and magnetic fields, currents. And it was a mathematical convenience to do so. You replace me with a bunch of those currents and then allow those currents to radiate, and voila, you've got the radar cross-section of Professor Durgan falling in free space. And you could identify who that is on your F-19 or whatever fighter. You shoot your electromagnetics teacher down. Definitely the enemy. But of course, that is purely mathematical convenience. We don't actually use anything like that in real life. We don't observe anything like that in real life. They're like these really goofy quantum mechanical physicists that say, well, beneath the envelope of uncertainty there are magnetic charges, and we're going to make a physics that behaves as such. I don't understand that stuff. I don't understand if that even helps you with anything. Let's see. You first.
Just a really quick question about the magnetic field or flux density unit. Is that the same as a Tesla? Because in another class we call that a Tesla.
Yes. Yes.
The Weber per meter squared, that's a Tesla, isn't it?
I believe that is. A Weber per meter squared is a Tesla. Okay. You can get yourself into a huge amount of trouble with magnetic units because you've got Webers, Teslas, Orsteds, what are some other ones? Gausses. In this class, I like the Weber or the volt second because it shows clearly that that's a flux density. Weber is the unit of flux. A flux density should have the units per meter squared. And so as a result, I kind of like that better. If you want to use something else, that's fine. I won't take off for it, as long as it's correct. And call it a Tesla. Knock yourself out.
Won't forget nothing.
So yeah. Lamb.
So I think I understand where I was getting confused, because this is a magnetic charge, kind of like an electron has a electric charge. So this is like something that has charge for magnetism.
That's right.
So,
You could make a Coulombs Law for magnetism, where I have a magnetic charge and there's B field radiating out of it. Well, it turns out we don't ever observe the B field radiating out of anything. The divergence is always equal to 0. The sourciness is always equal to 0. And so there can't be anything like a magnetic charge. It can only circulate around current. That's right. Oh, yeah.
You said that here with the surface integral of the current density will give you amps, right?
That's right.
All right.
That's right.
Can you explain the units with the electric flux density?
Okay. So I've got, that's a good question. This equation, basically, right? How do the units track in this equation? So I'd say he was right to denote that the integral of magnetic field, which has amps per meter, around a path, which sort of brings in an extra meter into the calculation. So you have amps per meter times meters, that gives you amps. This is current, that has units of amps. And of course, if we wanted to see that, we say, though, this is amps per meter squared. I'm integrating it over a surface area. So this is going to bring in meters squared into the equation. Amps per meter squared times meter squared is also amps. This is a flux, electric flux density, integrated over a surface. So you have coulombs per meter squared integrated over an area, which is meters squared. So when you're done this integral, you have an electric flux, which is just coulombs. And when you take the derivative, it's coulombs per second, which is amps. Amps. Very good, very good. Okay. Any other questions so far? Now, think of how giddy Maxwell was when he put all these together. He was really excited. It's like putting together one of history's long, great puzzles. You know, we observed magnetic behavior and static electricity way back, literally millennia before this happened. And he was able to put this down and kind of unify all of electromagnetism. Everything that had been seen to that point could be explained by this in the macroscopic world as far as electrodynamics are concerned. It was like putting together a beautiful puzzle. How many people have ever put together like a 1,000-piece puzzle before? Yeah, it was pretty cool. Did you feel like really gratified when you put it together? How many people were so gratified that they actually like shellacked it and put it on a little cardboard or maybe a plywood and maybe framed it and hung it in their room? Anybody who did that? Raise your hand. Good. No, you and I are very kindred spirits, all of you in this section. Good synthetical mind. You like to see the pieces come together. This was a beautiful, beautiful puzzle. But this is not the end of the story. Imagine if you had put together that beautiful 1,000-piece puzzle that made a nice picture, of a barn and a horse and flowers in a field or whatever, I don't know. You put that together and you think, I love this puzzle. It's so beautiful. I'm going to shellac it. I'm going to glue it all together. I'm going to eventually hang this in my room. So you go ahead and do that. You shellac it. You put it together. You put a frame around it. And now you got to put a backing. So you very carefully flip it over. That's usually what happens. It breaks. In this case, however, Maxwell discovered that he had inadvertently put together a far more beautiful puzzle on the backside. And that's what the next lecture is going to be about. And I'll give you a hint of what it is. It's the chain reaction that happens when you complete Maxwell's equations. Because now, a change in the magnetic field will change the electric field. A change in the electric field will change the magnetic field, which will change the magnetic flux, which will change the electric field, which will change the magnetic field, which will chain reaction. And now the wave is born. In fact, it would be 2 decades later until Guglielmo Marconi would prove that there were invisible waves out there, and he basically proved Maxwell right. That there are invisible waves out there that carry energy and later information, more importantly, which is the basis of all wireless technology. So you get, in this synthesis, not only do you get all of electricity and magnetism, you get optics, you get radio waves, you get X-rays, you get everything. You basically get the way that we transport energy and information, properly understood, the two not being that different from one another. energy and information in our universe. And so that's where we'll start with the next topic, which is the wave equation.